The changing seasons we experience annually represent just one layer in a complex hierarchy of climate cycles that operate across vastly different timescales. While most people understand that Earth's axial tilt creates our regular seasonal patterns, few appreciate how this tilt interacts with other planetary motions to produce much longer climate cycles that have shaped human evolution and geological history. These grand climatic rhythms, known as Milankovitch cycles, after the Serbian mathematician Milutin Milanković, who first systematically described them in the 1920s, emerge from subtle variations in Earth's orbital characteristics over thousands of years. They explain why our planet periodically plunges into ice ages, and why the timing of seasons slowly shifts across the calendar over millennia. Understanding these cycles provides crucial context for both Earth's climatic past and the potential trajectories of our climate future. At the most fundamental level, Earth's climate variations stem from how solar energy gets distributed across the planet's surface. The total amount of energy Earth receives from the Sun remains remarkably constant. What changes is where and when that energy arrives. Three primary orbital characteristics govern this distribution: eccentricity, the shape of Earth's orbit around the Sun; obliquity, the tilt of Earth's axis relative to its orbital plane; and precession, the slow wobble of Earth's rotational axis. Each of these parameters vary cyclically over different timescales, creating complex interference patterns in Earth's climate system. The 100,000-year eccentricity cycle, the 41,000-year obliquity cycle, and the 26,000-year precession cycle interact to produce the major climatic variations we see in the geological record. The eccentricity cycle, operating on a 100,000-year timescale, describes how Earth's orbit oscillates between more circular and more elliptical shapes. Currently, Earth's orbit is nearly circular, with only about 3% difference between its closest, perihelion, and farthest, aphelion, points from the Sun. However, at maximum eccentricity, this difference can reach nearly 30%, significantly altering the solar radiation Earth receives at different points in its orbit. What makes this cycle particularly important for climate is how it interacts with the precession cycle, the timing of when these orbital extremes occur relative to Earth's seasons. Currently, perihelion occurs in early January during Northern Hemisphere winter, meaning our winters are slightly milder than they would be otherwise. But this configuration slowly changes over thousands of years due to precession. Obliquity, or axial tilt, represents perhaps the most intuitive of the Milankovitch cycles. Earth's current 23.4-degree tilt relative to its orbital plane creates our familiar seasons. However, this tilt varies between about 22.1 and 24.5 degrees over a 41,000-year cycle. When the tilt is greater, seasonal contrasts become more extreme. Summers become hotter and winters colder in both hemispheres. Reduced tilt leads to more muted seasonal differences. Currently, Earth's tilt is decreasing from its maximum, meaning we're in a phase of gradually less extreme seasonal variations. This might seem like it would lead to warmer conditions overall, but paradoxically, the geological record shows that ice ages tend to begin when tilt is decreasing, because milder summers allow winter snow accumulation to persist year-round in high latitudes, beginning the process of ice sheet growth. The precession cycle, sometimes called the wobble of Earth's axis, completes the Milankovitch triad. Over about 26,000 years, Earth's rotational axis traces a circle in space, much like a spinning top winding down. This means that which celestial pole star we have, currently Polaris, changes over time. And more importantly for climate, it changes which hemisphere experiences summer when Earth is closest to the Sun. Today, the southern hemisphere has summer at perihelion, receiving about 7% more solar radiation during its summer than the northern hemisphere does. In 13,000 years, this situation will reverse, with the northern hemisphere gaining the advantage of summer at perihelion. This cycle is particularly important because it determines whether the amplification of solar radiation from eccentricity affects summer or winter in each hemisphere. The interaction of these three cycles creates the complex pattern of climate variation seen in ice core and sediment records. For instance, the 100,000-year cycle of ice ages that has dominated the past million years appears to result from a particular combination of eccentricity, obliquity, and precession that allows ice sheets to persist and grow in the northern hemisphere. The relatively weak 100,000-year eccentricity cycle appears amplified in the climate record because of feedback mechanisms in the Earth's system, particularly the reflectivity, albedo, of expanding ice sheets and the atmospheric concentration of greenhouse gases that vary in sync with these orbital changes. Understanding these cycles requires examining how they affect solar radiation distribution across Earth's surface. Astronomical calculations show that summer insolation, incoming solar radiation, at 65 degrees north latitude appears particularly important for ice sheet growth and retreat. When summer insolation at these high northern latitudes falls below a certain threshold, winter snow accumulation can survive through the summer, beginning the process of ice sheet growth. The current configuration of Milankovitch cycles suggests we're in a relatively stable interglacial period that would typically last about 10,000 to 15,000 more years before the next glacial period begins. However, the unprecedented rise in greenhouse gas concentrations from human activities has introduced a wild card into this natural cycle. The geological record provides compelling evidence for the influence of Milankovitch cycles. Deep-sea sediment cores show regular variations in oxygen isotope ratios that reflect changes in global ice volume over the past several million years. These records reveal that the dominant periodicity of ice ages changed about 1 million years ago from a 41,000-year cycle, matching obliquity, to a 100,000-year cycle, matching eccentricity, in what scientists call the mid-Pleistocene transition. The reasons for this shift remain debated, but likely involve long-term cooling trends that made ice sheets more sensitive to particular orbital configurations. Modern climate science continues to refine our understanding of how Milankovitch cycles interact with other climate forcings. While these orbital variations provide the pacemaker for ice age cycles, they work in concert with greenhouse gas concentrations, ocean circulation patterns, and tectonic changes to produce the actual climate variations we observe. The relatively weak changes in solar radiation from orbital variations get amplified by feedbacks in the climate system, particularly through changes in ice cover, vegetation patterns, and atmospheric composition. This explains why the 100,000-year eccentricity cycle, which produces only minor changes in total annual solar radiation, can nonetheless drive massive glacial-interglacial cycles. The implications of Milankovitch theory extend beyond academic interest. Understanding these natural climate cycles helps contextualize current anthropogenic climate change against Earth's longer-term variability. It also provides insights into potential climate futures, both the natural cooling trend we might expect over the coming millennia in the absence of human influence, and how anthropogenic warming might interact with these natural cycles. As we continue to alter Earth's atmosphere and surface, the lessons from Milankovitch cycles remind us that small, sustained changes to Earth's energy balance can produce dramatic climate transformations over time. The apparent contradiction between the modest variations in solar radiation caused by Milankovitch cycles and the dramatic climate shifts they produce represents one of the most fascinating puzzles in paleoclimatology. While Earth's orbital parameters change only slightly over millennia, these subtle alterations somehow trigger continental-scale glaciation and deglaciation events that reshape entire ecosystems. This amplification occurs through a series of powerful feedback mechanisms that transform small astronomical nudges into global climate revolutions. The transition from interglacial warmth to ice age conditions typically begins when orbital configurations lead to slightly cooler summers in critical northern latitudes, just enough to allow winter snow accumulation to persist through the warmer months. What begins as a minor change in seasonal snow cover escalates into a planetary-scale transformation through three primary amplifiers: the ice albedo feedback, the greenhouse gas feedback, and ocean circulation changes. The ice albedo feedback provides the most straightforward amplification mechanism. As ice and snow accumulate, they increase Earth's albedo, causing more incoming solar radiation to bounce back into space rather than being absorbed as heat. This cooling allows ice sheets to expand further, increasing albedo even more in a self-reinforcing cycle. Climate models suggest that this feedback alone can triple the initial cooling from orbital changes. During the last glacial maximum, about 20,000 years ago, ice sheets covering much of North America and Europe increased Earth's albedo by about 30% compared to today, reflecting enough sunlight to lower global temperatures by an additional 4 to 5 degrees Celsius beyond the direct effects of reduced summer insolation. The growth of these ice sheets wasn't gradual. Geological evidence shows they expanded in rapid pulses when certain climate thresholds were crossed, demonstrating the non-linear nature of ice albedo feedbacks. Equally important is the greenhouse gas feedback, which acts in concert with ice albedo effects. Ice core records from Antarctica reveal an astonishingly tight correlation between atmospheric CO2 concentrations and global temperatures over the past 800,000 years. During glacial periods, CO2 levels dropped to about 180 parts per million, compared to pre-industrial levels of 280 ppm. While during interglacials, they rose to 280 to 300 ppm. This variation accounts for roughly half of the temperature difference between glacial and interglacial conditions. The mechanisms linking orbital forcing to CO2 changes involve complex interactions between the atmosphere, oceans, and biosphere. Cooling oceans absorb more CO2, while expanded ice sheets reduce the area available for plant growth, decreasing carbon storage in terrestrial ecosystems. Changes in ocean circulation patterns may also affect the rate at which deep ocean carbon reservoirs exchange with the atmosphere. These processes create another powerful positive feedback loop, where initial cooling reduces atmospheric greenhouse gases, which causes further cooling. Ocean circulation patterns provide the third major amplifier of Milankovitch forcing. The Atlantic Meridional Overturning Circulation, AMOC, which includes the Gulf Stream, plays a particularly crucial role in climate transitions. As ice sheets grow and freshwater input to the North Atlantic increases from melting icebergs, the AMOC can weaken or even collapse, dramatically reducing heat transport to northern latitudes. Paleoclimate evidence shows that such disruptions occurred repeatedly during the last glacial period, causing abrupt regional cooling events of up to 10 degrees Celsius in just decades. These ocean circulation changes help explain why Milankovitch forcing affects climate differently in various regions. While orbital changes distribute solar energy relatively evenly across the globe, their effects get channeled through ocean and atmospheric circulation patterns that create strongly regionalized climate responses. The tropics, for instance, experience relatively small temperature changes during glacial cycles, but significant variations in precipitation patterns. The timing of ice age cycles relative to Milankovitch forcing reveals another layer of complexity. Detailed analysis of ice core records shows that changes in greenhouse gas concentrations and global temperature often lag behind the orbital changes that initiated them by several thousand years. This lag occurs because the growth and decay of massive ice sheets represents a slow physical process. It takes time for accumulated snowfall to compress into ice and flow outward into continental-scale glaciers. Similarly, the ocean's thermal inertia means that surface temperatures respond gradually to changes in solar forcing. However, once certain thresholds are crossed, climate transitions can occur remarkably quickly. The end of the last ice age featured several instances where global temperatures rose 5 to 10 degrees Celsius in just a few decades, likely triggered by sudden reorganizations of ocean circulation or rapid ice sheet collapse.
The mid-Pleistocene transition, which occurred about 1 million years ago, marks a crucial change in how Milankovitch cycles affected Earth's climate. Before the MPT, ice ages followed a 41,000-year cycle, matching the obliquity period. Afterward, they shifted to a 100,000-year cycle, matching eccentricity. This transition remains incompletely understood, but likely involved long-term cooling that made ice sheets more sensitive to particular orbital configurations. One theory suggests that gradual atmospheric CO2 decline made the climate system more responsive to eccentricity variations. Another proposes that glacial erosion changed the bedrock topography beneath northern hemisphere ice sheets, making them more stable and long-lasting once they formed. Regardless of the exact mechanism, the MPT demonstrates that the relationship between orbital forcing and climate response evolves over geological timescales. Modern climate science continues to refine our understanding of these feedback mechanisms through increasingly sophisticated computer models. These models can simulate how small changes in solar forcing get amplified into full glacial interglacial cycles, helping identify which feedbacks matter most under different conditions. Recent work suggests that atmospheric dust levels may represent another important amplifier. As ice sheets expand, they create drier conditions that increase dust deposition on remaining ice and snow, reducing their reflectivity and accelerating melting. This negative feedback may help trigger the relatively rapid deglaciations seen in the paleoclimate record. Other studies focus on how vegetation changes interact with ice sheet growth, as expanding tundra replaces forests at high latitudes, further increasing surface reflectivity.
The implications of these feedback mechanisms extend beyond academic interest. They demonstrate that Earth's climate system contains multiple tipping points where small, gradual forcing can produce large, rapid changes. This understanding informs contemporary climate change research by showing how anthropogenic warming might trigger similar feedbacks in reverse. Melting Arctic sea ice reduces albedo, warming oceans release CO2, and thawing permafrost emits methane. While the current human-driven warming occurs much faster than natural orbital changes, the paleoclimate record provides crucial evidence about how Earth's climate system responds to various forcings over different timescales. Looking ahead, Milankovitch theory predicts that, in the absence of human influence, Earth would gradually cool over the next 20,000 years toward another glacial period. The current interglacial period, the Holocene, has already lasted about 11,700 years, comparable in length to previous interglacials. However, the unprecedented rise in atmospheric CO2 from human activities has almost certainly disrupted this natural cycle. Climate models suggest that unless CO2 concentrations fall dramatically, the next ice age may be postponed by 100,000 years or more. This human intervention in Earth's astronomical climate rhythms represents an unplanned global experiment whose full consequences remain uncertain. The study of past Milankovitch cycles reminds us that Earth's climate has always changed, but also that human activities now rival astronomical forces as drivers of that change. The delicate interplay between Earth's orbital cycles and climate systems now faces unprecedented disruption from human activity, creating a new geological epoch where anthropogenic forces compete with celestial mechanics. For the past 2.6 million years, the Pleistocene's glacial-interglacial rhythm has pulsed to the beat of Milankovitch cycles. But our current Holocene interglacial period has developed a new tempo shaped by industrial civilization. This collision between astronomical and human-driven climate forcing presents a profound scientific and societal challenge: how to reconcile the natural rhythms that have governed Earth's climate for millions of years with the rapid changes induced by greenhouse gas emissions. The paleoclimate record suggests we should currently be in a period of very gradual cooling, with summer insolation at 65 degrees north having peaked about 11,000 years ago and slowly declining toward conditions that might, in several thousand years, favor the growth of continental ice sheets. Instead, human activities have reversed this trend so dramatically that current CO2 levels at 420 parts per million exceed anything in the past 3 million years, effectively short-circuiting the natural progression toward the next ice age. This human intervention in Earth's astronomical climate cycles raises fundamental questions about how natural and anthropogenic forcings will interact in coming centuries. Climate models incorporating both Milankovitch cycles and projected greenhouse gas scenarios suggest that the next glacial inception, which might normally occur in about 50,000 years under natural conditions, could be delayed by 100,000 or more, depending on emission trajectories. The duration of this postponement depends critically on how long elevated CO2 persists in the atmosphere, a factor complicated by various carbon cycle feedbacks that are still not fully understood. Deep ocean sediment studies show that during past interglacials with similar orbital configurations to today, particularly marine isotope stage 11 around 400,000 years ago, interglacial conditions persisted for 20,000 to 30,000 years, nearly twice the length of typical interglacials.
This geological precedent suggests that even without human influence, the current interglacial might have been exceptionally long, but anthropogenic warming has taken this possibility to extremes beyond anything in the Pleistocene record. The concept of planetary boundaries provides a useful framework for understanding how human activities interact with Milankovitch cycles. Researchers have identified 9 critical Earth system processes that maintain the stable Holocene conditions which enabled human civilization to flourish, with climate change and biosphere integrity considered core boundaries. Milankovitch forcing traditionally operated well within these boundaries, causing climate variations that, while significant, remained within limits that allowed ecosystems to adapt through migration and evolution. Human-driven climate change, by contrast, is pushing the system toward thresholds that may trigger irreversible changes on timescales irrelevant to traditional astronomical cycles. The rate of current CO2 increase is about 100 times faster than the most rapid natural rises seen in ice core records, leaving insufficient time for many species and ecosystems to adapt. This creates a peculiar situation where we are simultaneously preventing the next ice age while potentially creating climate disruptions more severe than typical glacial-interglacial transitions. The relationship between Milankovitch cycles and contemporary climate change also informs debates about climate sensitivity. How much global temperature changes in response to radiative forcing? Paleoclimate evidence from past interglacials suggests that Earth's climate system is highly sensitive to relatively small changes in energy balance when certain thresholds are crossed. During the transition out of the last ice age, for example, a mere 0.3% increase in total solar radiation reaching Earth triggered a 5 degrees Celsius global warming through powerful feedback mechanisms. This historical precedent raises concerns that human-caused forcing may similarly engage feedbacks that amplify warming beyond what basic greenhouse gas concentrations would predict. Current observations already show these amplifiers at work. Declining Arctic sea ice reduces albedo, melting permafrost releases methane, and warmer oceans hold less CO2. All reinforcing the initial warming trend in ways reminiscent of, but much faster than, natural interglacial warming periods. Milankovitch theory also provides insights into regional climate patterns that may emerge under anthropogenic warming. Paleoclimate data show that orbital forcing affects precipitation patterns differently in various parts of the world, with monsoon systems being particularly sensitive to insolation changes. During periods when Northern Hemisphere summer insolation was stronger than today, as it was 8,000 to 10,000 years ago, the African monsoon was more intense, creating a green Sahara with extensive lakes and savanna vegetation where there is now desert. These past conditions, caused by orbital configurations that enhanced seasonal temperature contrasts, provide potential analogs for how regional rainfall patterns might shift under human-caused climate change. However, the rapid pace of current warming and the different spatial pattern of radiative forcing, greenhouse gases distribute heat differently than orbital changes, mean that exact paleoclimate analogs may not exist for the coming century. The long-term perspective provided by Milankovitch cycles also helps contextualize debates about climate stabilization targets. The Paris Agreement's goal of limiting warming to 1.5 to 2 degrees Celsius above pre-industrial levels represents a deliberate attempt to keep Earth's climate within the range of variability experienced during the Holocene. However, Even this safe range includes temperatures warmer than any point in the past 120,000 years, and sustained CO2 levels above 350 ppm may already commit Earth to changes outside the envelope of recent interglacials. Climate models that incorporate both Milankovitch forcing and anthropogenic emissions suggest that unless CO2 is actively removed from the atmosphere, the current interglacial climate state could persist for tens of thousands of years longer than natural cycles would dictate, potentially skipping the next 1 to 2 glacial periods entirely. This would represent one of the most lasting and conspicuous human impacts on the Earth system, visible in geological strata millions of years hence.
The study of Milankovitch cycles in the Anthropocene also raises profound questions about humanity's relationship with deep time. For the first time in Earth's history, a single species has developed the capacity to alter planetary-scale climate processes that were previously governed solely by astronomical and geological forces. This power brings with it responsibility to understand the climate system we are disrupting, to anticipate the consequences of our actions across multiple timescales, and ultimately to decide what kind of climate future we want to create. The paleoclimate record shows that Earth's climate can exist in multiple stable states, glacial and interglacial being just two, and that transitions between these states often occur rapidly once certain thresholds are crossed. As we push the climate system beyond the range of natural variability documented in ice cores and ocean sediments, we risk triggering changes that could persist for millennia, long after any conceivable fossil fuel era has ended. Looking ahead, the integration of Milankovitch theory with climate change research will likely focus on several key areas. Improved understanding of carbon cycle feedbacks will help predict how long anthropogenic CO2 will remain elevated, and how this might affect future orbital-scale climate evolution. Better reconstructions of past interglacials will provide crucial data points for how Earth's climate behaves under slightly warmer conditions than the Holocene. And refined climate models will continue to explore how orbital forcing and greenhouse gas changes interact across different timescales. Perhaps most importantly, the long-term perspective provided by Milankovitch studies reminds us that climate change doesn't end in 2100. The decisions we make today about energy systems and emissions will shape Earth's climate trajectory for tens to hundreds of thousands of years, potentially overriding the natural astronomical rhythms that have governed ice age cycles for millions of years. In this context, the current geological epoch represents not just another turn of the celestial climate cycle, but a fundamental transformation in how Earth's climate functions. A transformation where human choices now rival orbital mechanics as determinants of planetary climate destiny.
The slow, rhythmic dance of Earth's axial tilt, oscillating between 22.1 degrees and 24.5 degrees over 41,000 years, has long dictated the pulse of our planet's climate. Today, we find ourselves in an epoch of transition, not just astronomically, but anthropogenically. The current tilt of 23.44 degrees, now gradually decreasing since its peak in 8700 BCE, would naturally guide Earth toward cooler summers and the slow accumulation of ice sheets over millennia. Yet human activity has disrupted this ancient rhythm, injecting greenhouse gases into the atmosphere at a rate that dwarfs the incremental changes driven by orbital cycles.
The Holocene's relatively stable climate, which nurtured the rise of civilization, is giving way to the Anthropocene, an era where human influence rivals the gravitational forces that once solely governed Earth's climate destiny. The interplay between Milankovitch cycles and anthropogenic warming presents a paradox. On one hand, the current phase of decreasing obliquity might have otherwise set the stage for a gradual return to glacial conditions, with milder summers allowing snow to persist at high latitudes. On the other, the sheer magnitude of human-caused warming has overridden these subtle astronomical cues, potentially delaying the next ice age by tens of thousands of years. This divergence underscores a profound truth. While Earth's orbital mechanics still operate with the same celestial precision, their climatic influence is now mediated and in some cases muted by human activity.
Yet, the legacy of Milankovitch cycles endures. They remind us that climate change is not a novel phenomenon, but a fundamental feature of Earth's history. The difference now lies in the speed and scale of change, as well as our unique capacity to comprehend and alter these processes. As we peer into the future, the lessons of these cycles offer both caution and hope. Caution, because they reveal how small perturbations can cascade into planetary-scale transformations through feedback loops like ice albedo and greenhouse gas amplification. Hope, because they demonstrate Earth's resilience and the possibility of finding equilibrium, even after dramatic shifts. The angle of Earth's axial tilt, now midway through its 41,000-year journey, will continue its silent sway, indifferent to human affairs. But for the first time in 4.5 billion years, a species has emerged that can read these cosmic rhythms, foresee their consequences, and choose whether to harmonize with them or rewrite their score. The challenge ahead is not just to mitigate climate change, but to align our actions with the deeper temporal wisdom encoded in Earth's orbital cycles. In doing so, we might yet forge a future where humanity's brief but fiery epic leaves behind not just disruption, but a renewed appreciation for the delicate balance that sustains life on this pale blue dot, suspended in the grand celestial symphony.